it's for fun. But this is the thing that's causing me trouble, right? And I told you I'm really worried about the negativity here destroying everything, right? But when before this time, this thing can never is always, this sum is bounded by n. And so sigma n, first of all, sigma n is less than equal to n. Because as soon as, it's even n minus 1, because as soon as little n gets to the value n, I've got a 1 there, g is greater than or equal to 0. So the sum is already n plus 1, which is bigger than n. So so it's less than n, maybe less than n minus 1. But also, now I can take tau n to be equal to whatever tau I started with and minimize it with sigma n. And that's also a stopping time. Okay, now these are things I'm telling you, and this would have to be an entire course on the mathematics of martingales and Markov chains to prove everything. But the minimum of stopping times is a stopping time. It really does fall from the definitions. If you go back and review the definition, which I don't intend to do. And guess what? For this stopping time, this condition holds. And so you get this, so I can apply this simple fact. So I know that the expectation of that monster over there is greater than or equal to the expectation of m0, and that's equal to that horrible monster there. And I could put a little x there if you want, just emphasize that I'm initializing at time x. And m0, I guess maybe I didn't define, but it's all consistent. For n equals 0, I'm summing from 0 to minus 1. No, I'm not. It's just v of x0. It's all consistent. Okay, so maybe I forgot to say that, but in M0, there's a definition, it's consistent. You have the super martingale property. So the trick here is that it would be really dangerous working with this if I didn't stick in that minimization there, because I could have infinity minus infinity. But I know that this thing here, g is positive, and the sum up to this thing is less than n. So that guy's finite. This guy could still be infinite in some funky world. Unlikely in our world. The f would have to have it take on infinite values or something. But hold on. But this thing is bounded below, so we don't have infinity minus infinity. And that allows me to take this to the other side. And you see that's what I want, because I want g on the other side. Yep.
Why is 0 less than the time at tau?
What's that?
The bottom line. So the expected value of m0 less than towards the left.
No, that's my simple fact. Oh, I'm sorry, did I go the wrong direction? M0 is bigger, yeah. Thank you. Yeah, I just, yeah. Okay, that's what I want. So I've got my v of x, something's less than v of x, and now I shuffle things around. I can kill this, can't I? So you almost get what you want. And I can write down a consequence really nicely. I've got, I'm going to write it like this. The expectation of the indicator function tau less than infinity, I'm throwing this in for the fun of it. I'll explain in a second. And so now I'm taking the G part and taking it to the other side. I know, this is a workout. Why did I do this? Well, I can, first of all. This is, again, this logic function, which is 1 if this event is true and otherwise. I didn't tell you that we don't even know if tau is finite valued yet. So tau is going to be maybe a first hitting time to some set. And this result is even true if we don't know a priori that the stopping time takes finite value. So it could be infinity with positive probability, and this theorem still holds. Okay, I didn't tell you that, but it holds. Now, what I can do is, there's a bunch of results. That's true. Yeah, I shouldn't have done that. I assumed it was finite. Let's keep that assumption. I take it back. This is true. I'm trying to prove more than I actually stated. Why do that? That's one. Just ignore that. Just forget. I just realized I shouldn't try to prove everything. We've assumed tau is finite value. Let's stick to that. Now, does anybody ever heard of Fatou's lemma? You have. Well, there's something called Fatou's lemma, which allows me to take a limit. There's Fatou's lemma that says let's see, hold on a second. Okay, so Fatou's limit says that the thing I care about, which is I want to take a limit inside, let n go to infinity, no n. The thing that I really care about is less than the limit infimum of the left-hand side. So maybe this doesn't converge as n goes to infinity, but you look at its lower limit as n goes to infinity. But then I look at the right-hand side, and remember, I assume G is non-negative. So the right-hand side does converge because this is a non-decreasing sequence. As n gets bigger and bigger, this gets bigger and bigger, And so the right-hand side how do I say this compactly? Well, anyway, let's keep going. So the thing I care about is less equal to the limit infimum of the left-hand side, right? And there's a less than sign there. So it's less than equal to v of x plus the limit infimum of this thing. But that limit exists. that monster. Damn, I keep on. And that's the thing, is you need to take an entire course on stochastic processes to understand everything I'm saying. But when you have a monotone sequence like this, and you want to take limits, the limit exists and is equal to what you care about. And aptly put, that equality is called the dominated convergence theorem. Oh, no, monotone convergence theorem. Aptly put, as I said, not inaptly put, as I just put it, the monotone convergence theorem. Yeah. All right. So the dominant convergence theorem would hold if I knew this thing actually, the mean was actually finite. All right. So that's it, QED. All right. I've got the left-hand side is less than or equal to this by a result called Fatou. And if you've never heard of Fatou's lemma, don't worry about it. These are the tools you need, though. And that's exactly the left-hand side. And then this thing here, by another result, you get what you want. So incredibly, incredibly cool tools. And again, the usefulness of this is applying this to functions where f is something you really care about, like bounding a cost function you're interested in, and g is something you understand. You know? And so I'm just going to close with that.
So the Fatou's lemma right here, like I mean, it's the expectation of that quantity just because the lim_inf is equal to the limit here.
Yeah, I mean, just because of the fact that I said, now I'm going to assume that tau is finite valued. And so there was a lim_inf in there. And that's what that is, yes. For those of you who know what lim_infs are in Fatou's lemma, by assuming that tau is finite valued, I get this as the lim_inf inside. So basically, Fatou says that the lim_inf inside is less than the lim_inf outside. Yeah. But the way this is so okay. But you see, this is a machine that is used in this literature so much. You know, you construct a martingale, and you pick up a Paul and Heidi or some other book on martingales, and you find results. And there's all sorts of results on probability of some large excursions and things like that. Also, once you have a super martingale, there's just a million tools you have for analysis. And this is the crudest application of those tools imaginable. I mean, these are not deep tricks. But this is a powerful inequality. It's fucking awesome. It really is. And in the case of V3, I can kill all this. We have to remember there's no more black pen. So this thing here turns out to be really easy to understand in that case. Just think about it. So our tau was a first return time to some particular state. And this, if you just plug this in, b is a constant, you can take it outside. Stare at that for a minute. This is what you get from that thing there. I should have said this. I forgot to say this is called the comparison theorem. All right. So this thing here that's so mysterious, stare at this. So I'm counting the number of times I hit this finite set S up until returning to the state X bullet. It's a finite set, right? So first of all, it's 0, it's 0, it's 0, it's 0, it's 0. And then finally, I reach a state S. Well, maybe not. Maybe I saw this X dot before I got to S. So it's very likely the sum is 0, right? But then once I hit S, I get a point of 1. And I'm starting from S now. And I then recount, and I look at when am I going to get to X dot, and I'm 0, I'm 0, I'm 0, because I haven't hit S, I haven't seen S, I haven't seen X dot, I haven't seen S. I'm counting up zeros, and then say, I'm unlucky again, I hit S again. Now I've got a 2, and I've got another, it's almost like an independent trial. All right? So it's really easy, first of all, to see that this is less than or equal to B times the minimum, or maximum, I mean. So from those arguments, it's really easy to see this. And again, this I think I'm also going to stick in the next homework assignment for you to prove this using the shift operator ideas. I'll walk you through it. I'm tempted to do that. But it's intuitively, it's just what I said. This is 0 until I hit S. So you're not counting anything until you reach S. And then S is a finite set. So it's a good hint that this should be finite values. So this is finite. And that's a little deeper. And it's again, it's like an independence trials argument. You know, every time I reach S, there's a probability almost independent of the past that I'm going to hit X dot before I hit S again. So basically, it's like a, you know, there's a geometric trials argument. I'm not going to prove it. I'm not going to prove it, but there's via a geometric trials argument. Or operator theory in the notes. So you can prove that these results like that with a bit of operator theory, which you can find in the notes, but it's totally non-intuitive. And this is, I feel, more intuitive. You know, I mean, after all, this was just a generalization what we saw before with tau deterministic. So it's clear. All right, so that's that. I mean, that is that. So we've got just a few more things to do over the next few lectures on Markov models and things that I think are going to really come in value. But before we close, any other questions? Basically, that's it. I mean, combining this fact that I'm not proving, but it's true, with this beautiful result, we do have that theorem I gave you. But yep.
For V3,
yeah.
You said that's like the Poisson inequality we're going to use in this course. But is there?
I said it's a refinement of the Poisson inequality.
Yeah.
Yeah.
Is there like any super theorem inequality, like a theorem about that inequality that we can say anything more deeply?
No, there's a whole menu of.
You said there's like a whole menu.
Yeah, there's a V4. There's a DV3, there's a million. I can give you a whole menu.
There's like another theorem or something?
Millions of theorems.
Like
millions of theorems.
something else.
I mean, I'll give you another one. So if you have V3 twice, I'll put a square there. So why on earth would I want V, the second moment of that Lyapunov function? Well, then my gamma squared C is going to be less than something I can identify, the CLT variance. All right. I could give you a specific number here if you wanted to. And that's from the formulas that I gave you last time, that gamma squared c, remember, was twice pi of c tilde times h minus pi of c tilde squared. Given this stuff, you know, if I can get this inequality, then I've got bounds on the central limit theorem variance. I mean, that's just repeated applications of this V3. But V4 is something else, and it's if you want to get geometric convergence of the distributions to a steady state. And then dV3, for another lifetime. In your second life, you'll learn about dV3. and there's more. There's probably a dV4. I just haven't seen it yet. Yeah.